Module 2, Lecture 6, Research Design and Data Management. This lecture will focus primarily on models of research design with a bit of information on and reflection on statistical analysis of data. We start first with this slide that is showing us a table of the characteristics of some common experimental designs. On the left column we have design, the description and conditions for use, the advantages and the disadvantages. These are experimental designs such as completely randomized design, stratified design, randomized block design, and crossover design. Terminology that we may not recognize, and the challenge here, or the exercise here, is to read through these columns and see what we do recognize, what we don't recognize, and take one step closer to understanding the structurally organized approach to experimental design, and being able thereby to turn back upon our own research activities and try to determine exactly if and what type of research design we utilize. So the completely randomized design, subjects or research samples are randomized to treatment groups or conditions in such a way that each group or condition is equally likely. The advantages of this, it's simple to administer. One treatment period per subject, and there's no dropout problem. Obviously, this is geared more toward human studies in description. The disadvantages, the comparison of the treatments between rather than within subjects is all that you can accomplish. So you cannot compare within a subject because the subject is in the experiment only once. We do encounter this situation quite commonly in our areas of research in the biological sciences because we'll have a separate treatment group for each data set. Therefore, it really can't compare within subjects because we don't test the same bacteria, for example, in condition A as we do in condition B as we do in condition C, and so on and so forth. So we must realize those limitations in the interpretation of the data. If you're comparing only between treatments and you have nothing on the within, there is something lacking in the quality of that data. The stratified design, or the randomized block design, we see that there is a comparison, the description of this is that the subjects are randomized to treatments or conditions separately within each block or stratum. The comparisons made within the blocks, which are like units, often have smaller sample sizes required than for the completely randomized designs. So that's a major advantage. Smaller numbers of samples or subjects can be used. The disadvantage is that the extended duration for each subject, if the treatments are administered in time, thus dropouts are a problem. So we can see that if we were to try to accomplish this, and it took a long time for the studies to be completed because each test subject would have to be exposed to every single type of treatment. So it becomes rather difficult to interpret even in the end. Even though on paper it seems more idealistic, the more test procedures you throw at a single test subject, whether it's bacteria, rat, or human, the greater the likelihood that dropout will occur for one reason or another. Next, the crossover design. The subjects are randomized to sequences where each sequence contains all treatment groups. So this one is not so uncommon in our area of research, and it seems very much the same as what we were just describing for the randomized block design. Except in this case, every single animal or test subject does receive randomly, in a random sequence, C, B, A, or A, B, C, or B, C, A, and then you have data from each test subject for each of the study conditions. So the disadvantages, obviously, the dropouts are a problem similar to what we saw in the previous design. So the comparisons are made within subject rather than between subjects in this extreme design. And you can have a smaller sample, and it's required. Smaller sample is required than the completely randomized design. So as we proceed through these, we proceed from assigning single, or let's say individual test subjects to individual tests to a point of having blocks of conditions per individual test subject, to the point of having a true crossover design where every single subject is exposed to every single treatment. And you have to randomize the sequence of the treatments, because if test condition A creates a situation where you get a different response for test condition B and for test condition C, then, and if you treat every subject in the same sequence, then you're always going to get the same result, but you can't interpret the result. So if you randomize all of those, any possible contribution of one prior treatment condition to a subsequent treatment condition is present within the variation of the data. So in other words, it's ruled out because it is randomized. The disadvantages of the crossover design: the potential for carrying over from treatments into subsequent periods, as I said, and then the extended duration for each subject also becomes a problem. Finally, then, the split plot design. The first experimental factor is randomly allocated at the highest level of sampling, or plots, and subsequent factors are randomly allocated to lower levels of sampling, the subplots, and so on. The advantage of this: the comparisons of secondary factors are made at lower levels of sampling, which may be more precise than the primary level. Disadvantage: it's only applicable in special situations where the classification into plots and subplots is a natural one. This certainly seems to be a design quite foreign to our area. With the term plot, it almost thinks you could use it in agronomy. So absent other conditions, I would almost always advocate equal sample sizes for all treatment conditions in this design and all other designs, as well as the footnote for this on that initial design that we described. And of course, this is a very good recommendation across the board. Whenever you end up with different sample sizes, unequal sample sizes, there is impact on your subsequent statistical analysis, and it can be a very limiting factor and a restrictive factor even in many cases. Now we can discuss this table on a summary of experimental methodology. And as much as it is for me, this discussion will seem extremely foreign for all of you. Very unlikely that students, even the most advanced students in the biological sciences or the basic sciences, would be familiar with all of these types of research methodologies and designs. More likely a psychology student would be exposed to them through the series of courses that they take. Our exercise is to go through again to see what we can recognize as a type of experimental approach that we might take if we were to write a grant proposal to the National Institutes of Health and use one of these terms for the particular type of design that we were planning. Probably would be an oddity more so than a commonality. Our exercise, however, is to build our skills in experimental design, understanding that there is a strict structure that exists, and however distant we are from having a solid appreciation of that, there is a bit of a weakness in our abilities as a responsible scientist. So the column on the left is the aim of the research. The next column proceeding to the right is the name of the design. Then there is notation paradigm, and then comments on the research design. So first we see the aim is to attempt to explain a consequent by an antecedent. The name of the design is the one-shot experimental case study. So this obviously is a pre-experimental design. We are saying that X proceeds to not or O, I guess. In other words, an antecedent leads to a consequence. This is an approach that prematurely links antecedents and consequences, the least reliable of all experimental approaches. So the weakest of the pilot study designs is shown here. In one shot, we treated the test subjects in such a way and predicted an outcome, and we got that outcome. Not a very strong argument to support your claim, your hypothesis. Aim 2, to evaluate the influence of a variable. Then in this case, it's called a one-group pre-test, post-test design. So O to X and then to O. So this is an approach that divides a measure of change but can provide no conclusive results. Still, we see that we're changing conditions and observing what might be happening, but we're really have nothing to compare things to draw a strong conclusion. So remember our linkage table of spurious association to chance association to correlation to causal association. So we keep that in mind all the time. How can we draw any conclusion of those sorts from this type of a study? The third aim for pre-experimental design, to determine the influence of a variable on one group and not another. So this is a static group comparison. So we have two groups, X to O, and then in group 2 we have no treatment. So this would be like drug A and vehicle for drug A proceeding to some observation. Then we're beginning to see that there's a bit better of an experimental design arising from this. The comments, however, the weakness lies in no examination of pre-experimental equivalence of the groups, no baseline data for the group 1 and group 2. Then the conclusion is reached by comparing the performance of each group to determine the effect of a variable on one of them. So with no prior knowledge of the pre-experimental status, then your observation at the end has no background within which to fit the response of the groups of test subjects. Next, we're looking at true experimental designs with the columns being the same. So the aim number 4 is to study the effect of an influence on a carefully controlled sample. So there's the pre-test, post-test control group design. So we have the R with the two other groups where we have pre-existing information, and then they are put through the experimental procedure. So we have made observation 1, if you will, pre-test, and then test, and then post-test. We're only testing one variable in this case. So the influence on a carefully controlled sample. So this design has been called by Mooley in 1970 the old workhorse of traditional experimentation. If effectively carried out, this design controls for 8 threats to internal validity. So we are now challenged to question whether any research we ever do could stand up to this evaluation on 8 threats of internal validity for our experimental design. Aim 5, to minimize the effect of pre-testing. This is called the Solomon 4 group design. So we are observing beforehand or not observing beforehand, and then proceeding from there. So is there any effect of pre-observation on the post-observation is part of the question we're asking here. So this is an extension of the pre-test, post-test control group design, and probably the most powerful experimental approach. The data are analyzed by doing an analysis of variance on the post-test scores. So I think what we're seeing here is that if we don't know detailed information about our subjects beforehand, there's a weakness. If we must gather some pre-test information about our test subjects before we begin the actual experimentation, then we don't know what effect that may have on the post-test evaluation. So we would predict that if the pretest has no effect on the post-test outcome for testing the effect of the variable on this outcome, or this test factor on the outcome, to use our own terminology used typically in this class, then we would predict that this observation here would be statistically identical to, or not statistically significant, was the typical way we state it. Did I get that right? This one would not be significantly different from this one, and this one would not be significantly different from this one. Continuing on with the true experimental designs. Aim number 6, to evaluate a situation that cannot be pre-tested. So there obviously are instances where you cannot collect data on a pre-test basis from the test subjects. So if it's the case of organisms or microorganisms or larger organisms where they must be euthanized or destroyed to collect the data, you obviously can't get can't always get a pre-test data set on them, or some type of a baseline. So this is a post-test only control group design where we have randomly organized the samples before proceeding into the design that we have seen before. So it's to be used in situations that cannot be pre-tested. It's an adaptation of the last 2 groups in the Solomon 4 group design. The randomness is absolutely critical, and the probably the simplest and best test for significance of this design is the t-test. We're comparing 2 groups. Next, we can proceed to quasi-experimental designs. The aim 7 is to investigate a situation in which random selection and assignment are not possible. So this is non-randomized control group pre-test, post-test design. We get a pre-test value, introduce the variable, and get a post-test value on the test subjects. This is one of the strongest and most widely used quasi-experimental designs. It differs from experimental designs because test and control groups are not equivalent. In comparing the pre-test results, we will indicate the degree of equivalency between the experimental and control groups. So you have the pre-test data, and if they are significantly different, then you're in a bit of trouble, is the assumption there, right? So determine the next aim to determine the influence of a variable introduced only after a series of initial observations and only where one group is available. So this is a time series experimentation. So we are observing on the same set of individuals. So if there's a substantial change that follows the introduction of the variable, then the variable can be suspect as to the cause of the change. To increase external validity, there'd be necessary to repeat the experiment in different places under different conditions. Continuing with the quasi-experimental designs, aim number 9, to bolster the validity of the above design with the addition of a control group, the control group time series design. So here we're seeing this sequential testing where somewhere along the way the test variable, the test factor is introduced or in a control situation, and we're seeing if the ongoing measurements of the measured outcomes will be affected. So this is a variant of the above design by accompanying it with a parallel set of observations without the introduction of the variable and in other words, the experimental factor or the test factor. Aim number 10, a variant of the above design with purpose of controlling history in time design. This is the equivalent time series, so we are looking for, in a sense, a cumulative type of an effect. This is an on-again, off-again design in which the experimental variable is sometimes present, sometimes absent. Sachs in 1968 has extrapolated the design with 2 extensions explained in the text of the source of this table. Now we can talk about correlational and ex post facto designs. Aim number 11, to seek for cause-effect relationships between 2 sets of data. So correlational studies do have to be performed. Remember, we said that the progression of the association between test factor and outcome was rule out spurious association, rule out chance, establish correlation, and then establish causal association. So we could thereby assume or indicate that correlational analysis would be required as one of the satisfactory steps or satisfying steps to demonstrating causal association. Then this is a very deceptive procedure that requires much insight for its use. Causality cannot be inferred merely because a positive and close correlation ratio exists. So there are the other criteria that we had listed in a previous lecture for establishing the causal association. So if we have a strong correlation, obviously a statistically significant effect or change, strong correlation, and there's biological plausibility, temporal reasonability, reproducibility, and specificity, and so on and so forth. If all of those criteria are satisfied and requirements are achieved, then we have a strong argument for a causal association between test factor and outcome measure. Aim number 12, to search backward from the consequent data for antecedent causes. This is typically more of a almost like an epidemiological type of an approach, where we have the observed condition, and we look for the information in the realm of the origin of the phenomenon for the a nice direction of the research effort coming back, so that we have other possible directions and a strong possible direction. And this approach is experimentation in reverse. Seldom is proof through the data substantiation possible. Logic and inference are the principal tools of this type of a design. We would probably rarely find ourselves in a situation of doing this type of research. Let's go back to take a look at the footnote on this. The symbols of each paradigm are explained fully in the discussion of the design within the text of the source. Now we switch to another table, beating ourselves up with tables here, but if we don't take time to go through these, we don't gain any knowledge whatsoever. And this table is on the tests of hypotheses. Again, we stated that we might rarely find ourselves in our scientific disciplines actually testing an hypothesis, but still the exercise is valuable to develop our awareness of these approaches for experimental designs and actual mathematical evaluation of the data to test the experiment within the design parameters. So the table lists the hypothesis here, and the different types of data sets, scale, nominal, ordinal, and interval and ratio types of data are the rows. The columns, there'd be two independent samples that have equal variability or the same central tendency or proportion, or two correlated samples that have the same central tendency, or k number of independent samples that have equal variabilities and same central tendency, or k correlated samples that have the same central tendency, or two variables that are uncorrelated or independent or linearly related. So that's a lot of different types of hypotheses, but let's just go along and see what we can gain from this. So with nominal data, probability minus probability 1 minus probability 2 is normally distributed with this formula. Again, what we're seeing is the standard deviation being represented and the sample size in these formulas. So similar types of components of the experiment contributing to the assessment of the data values to determine the types of approaches for evaluating it. So the chi-squared test for the equality of several sample proportions is the type of a test for the k independent samples that have the same central tendency. And then for two variables that are uncorrelated or independent, the chi-squared test of independence, the likelihood ratio chi-square if tau minus c 1.3863 nt has chi-square distribution with r minus 1 k minus 1 degrees of freedom. I guess we'd have to review our notes on chi-square if we were going to run that type of a test. For ordinal data, under equal variable, the two independent samples that have equal variability, we'd run a test also sensitive to differences in the central tendency, or run a test also sensitive to differences in variability, such as the median test or the rank sum tests. For two correlated samples that have the same central tendency, the sign test would be used. For k independent samples that have the same central tendency, a median test or the Kruskal-Wallis test might be used. This is the test, one of the non-parametric measures that we'll discuss in a little more detail later, that you will see rather frequently in some of the literature that we tend to read in our areas of science. The K-correlated samples that have the same central tendency would require the Friedman test, sometimes called analysis of variance by rank. This is another test that you might see often for non-parametric types of data sets from related types of experimental designs. For two variables that are uncorrelated or independent, the contingency test of association or the test of hypothesis, that P sub naught equals 0. So these are foreign languages to us, and what we need to recognize is that some of these tests, like the Kruskal-Wallis test and the Friedman test, may appear in some of the literature that we read, and we at least need to be aware that that means they're working with ordinal data. It is not normally distributed, and it is a non-parametric test that is being used to perform the evaluation. And of course, we have discussed the for these types of data sets, the type of central tendency analysis that is performed, and the type of values that we look at for dispersion around the central tendency. In other words, medians and modes and quartiles. Obviously, median would be important for evaluating ordinal data such as this, and the type of graph that would be used, the whisker plot graph, showing the median and the 25th and 75th percentiles. This is the skill that we hope to extract from these exercises. For the interval or ratio, the F-test assumes normality of the population, so we're now proceeding closer to a parametric type of analysis of data sets. So several formula here that we're not going to spend much time with, but we do recognize this test statistic here, the x bar 1 minus x bar 2 over the standard. Well, this is different than what we had looked at before, but relatively the same. Doing the t-test for the t-test statistic, looking at the t-table for the distribution. So the N1 plus N2 minus 2 degrees of freedom when the samples are from a normal population of equal variances. So these are terms that we see and recognize. We understand variance, we understand equal. So if we do not have a normal population and equal variances, then we may not be correct if we are trying to run a parametric test on these. There's, for the two correlated samples that have the same central tendency, there's the Wilcoxon test for paired replicates. For large samples or small samples from normal populations, there's a test procedure that can be run and end up with a t-distribution with n minus 1 degrees of freedom. K independent samples that have equal variables. The Bartlett's test for homogeneity of variance can be used. We'll see this, an example of this a bit later. In a sense, testing for the normality of your data. If they have the same central tendency, then an analysis of variance, where we'll see that there is an F distribution if the samples are from the normal populations with equal variances. So if we passed the Bartlett's test and proceeded to an analysis of variance, it would be based upon Bartlett's indicating a normal population with equal variances. The K correlated samples that have the same central tendency, there'd be an analysis of variance of two-dimensional, assumes normality and homogeneity of variance, or two variables that are uncorrelated or independent. Then the test the hypothesis that alpha, or nu equals 0 by use of the OF ratio, and test the hypothesis P equals 0 by the use of the F ratio or t-test. Completely foreign language to us. Or if they're linearly related, then test the hypothesis that P equals nu by use of the F ratio. Most importantly, what we're beginning to see is this F test emerging, a t-test and an F test statistic value that are calculated, and that's more of our focus of these efforts at this time. We can then take a look at another table viewing the parametric methods for continuous data, or hypothesis testing methods based on the normal theory. So what we're doing now is moving farther away from what seems the most foreign type of language and concepts in these discussions to something that feels a little more familiar to us, and realize what we don't know and what we do know, and move toward the future of improving our background in all of these areas. None of us will become an expert from these exercises, obviously, but we do get the opportunity to recognize what we do know and put it within the framework of what is known. It's always a good situation to be in. When you're in a situation where you don't know what you don't know, and you don't know that you don't know, you're in a pretty tough spot. So here then we see the first column on the left is the application, data description, the statistical methods, and then comments. So the first application is to test the hypothesis about the mean of a single population. In a future lecture, we'll go through the mathematical formulae for performing these procedures. We're introducing them now, so we'll see them at least one more time as we go through the formulae and build on an awareness of the basic statistical approach that builds up to the most commonly used statistical procedures in our areas, which are typically either the t-test or an analysis of variance, comparing two or more treatment groups. So it's not very often that we are testing the mean of a single population from a single sample, but this would be a t-test that would be used for that. Next, to test the hypothesis about the difference in means. So this is getting closer to a type of an experiment that we might perform. We have to understand whether it is paired or unpaired data. This would be for paired data. Then it would be the t-test with the paired data. And comment on this: one sample t-test after taking differences for each pair is the approach used here. Again, we'll run through all of this in a future lecture, trying to build our awareness of what these terms, these words all mean. So next, to test the hypothesis about the difference in two means. Here then we're going to have two independent samples, and with this we would perform the two-sample t-test. Next, to test the global hypothesis of differences among means. Now that we are using the term among, we know that it's going to be 2 or more independent samples. Then this is when we proceed to an analysis of variance, which has the acronym ANOVA, provides a global test, but it may not be optimal. There has to be another test that would follow that, called a post hoc test, to test for the comparison between the groups. And this is the next situation, the comparisons with the control or standard or pairwise comparisons. So for the comparisons with the control or standard, there's more than 2 independent samples. The Dunnett's test would be used, or the pairwise comparisons, where there's more than 2 independent samples. This would be the multiple comparison tests. The Student-Newman-Cools is a very common multiple comparisons test, and we'll look at a variety of these. Generally, we encounter the 2-sample t-test if there are only 2 independent samples. If there are more than 2, typically, we will see the analysis of variance, one sort or another, followed up by some type of a post hoc test to compare the treatment groups. Next, we see testing for a dose response. This is not always so common in the literature. People will test different doses of agents and end up using an analysis of variance with a post hoc test, as we had seen before. These are not the true statistical approaches for testing for a dose response. This is where there's several independent samples at different dose levels, and there are trend tests that are most appropriate for this type of an analysis. You'll rarely see that in the literature that we evaluate. And remember, the dose response was one of the primary means for substantiating biological plausibility and as well reinforcing the temporal reasonability in establishing a causal association. So if the wrong statistical test is used, then this biological plausibility argument is weakened to some degree. You know, the eyes are what we entrust. If we look at the means and the standard error bars and understand the data the way that we have struggled with in the prior lectures, then we can judge basically for ourselves whether there might be something real there. If in this case a trend test was not performed, we may not completely invalidate the data if there's a statistical significant ANOVA and some of the group comparisons are substantiated by the post hoc analyses, as we had seen before. Then there's testing for treatment differences. So these are becoming more and more complex with multifactorial or other types of extended designs. Then there will be a type of ANOVA with additional comparisons. We don't often see this in our area of research. Now then, we can go to the next table and look at non-parametric methods for continuous data. This is the hypothesis testing methods. So first in the application, data description, statistical methods, and comments again. We test the hypothesis about the location or the mean of a single population. Then this is data from a single sample. The Wilcoxon signed rank test would be used. Or if we test the hypothesis about the difference in means, where there'd be paired data. These are sounding very familiar to what we saw for the parametric table before, but the statistical method differs. The Wilcoxon signed rank test with paired data, commenting that one sample test after taking differences is performed for each pair. Next, to test the hypothesis about the difference in 2 means, 2 independent samples, then the Wilcoxon test would be used. To test the global hypothesis of differences among means, where 2 or more independent samples are present, then the Kruskal-Wallis test would be used. So what we're beginning to see is that the Wilcoxon test is similar to the t-test, the Kruskal-Wallis test is similar to the ANOVA, and the Dunn's test and other multiple comparison methods are equivalent non-parametric post hoc analyses tests. So the Kruskal-Wallis provides a global test, but may not be optimal. Typically has to be followed up with another test, a post hoc test for significant differences between the treatment groups. So there can be comparisons with a control or a standard, or a pairwise type of a comparison, as we saw in the previous table. As well, there are also non-parametric tests for testing for dose response, and the Jonquière trend test would be used. Testing for treatment differences. There are a wide range of analysis of variance on the ranks with additional comparisons needed. Now notice the ranks here. So we're looking at non-continuous data, not non-normal data, that may just have a maximum value and actual values like 1, 3, 5, something like that. So there has to be a ranking of these, and we are asking questions whether one is different from another based upon a ranking. Well, that certainly keeps our mind churning away on more so what we don't know than what we do know. And our objective through the next set of lectures and the last few slides of this lecture are to develop a substantial familiarity within ourselves for at least what we see most commonly within our arena of research activities. So let's look at some of the summary steps in a statistical analysis. Key punch the data. Well, many of the data acquisition instrumentation that we work with puts our data sets directly into either a text file for importation into a spreadsheet, or directly into a spreadsheet such as Microsoft Excel. Second, examine the data to get an overview, check for errors. This is very important. If you don't look at your data at this point for inconsistencies and errors and erroneous data points that must be excluded before you proceed justifiably, then you're going to have to do it later. Best to do it first. You check the assumptions of the normality or equal variances for continuous variables. So substantiate that you do have indeed permission to proceed with the type of analysis that you had intended. And then you compare the groups at baseline if you have that baseline data. Compare the groups of the variable on the variable of interest. And we saw the different approaches to this. Obviously, this isn't accommodating all of them, but we can see what we mean here. We determine the effect size, the size of the difference between the groups, and its 95% confidence interval. This is something we don't necessarily always perform ourselves, but we do calculate the effect size just to satisfy our own curiosity, if for nothing else. How much of an effect did I have is the question we're going to ask, obviously. We choose a statistical test by answering the following questions. Again, this should have been done before the experiment was proposed and initiated. What is the scale of measurement of the variable of interest? If the variable is continuous, is it normally distributed in the study population as a whole? How many groups are there? For 2 or more groups, are the subjects from the groups independent, unpaired, or matched, paired? We'll continue to build on that terminology. For a continuous variable, are the group variances equal? So we recognize these as being important from the tables that we just examined closely. Then run the chosen statistical test. Make sure you've got your data table set up appropriately for the statistical test that you're going to run, if obviously you're going to run a statistical software package on the data set. Reach a statistical conclusion. If P is not significant, was the power of your analysis adequate? This is a table from one of the listed supplemental textbooks on the syllabus, and it is based upon choosing a test It is a series of question-answer approaches to determine what statistical test you would use. We'll see this again in a future lecture, but let's just go through it rather quickly right now. First, we ask, are we working with a scale, normal, then the number of groups, then are they paired, and what about the variances? So whether it's scalar or normal, we ask, okay, normal, continuous, normal or non-normal. If it's continuous and non-normal, we shift over to ordinal. Or is it discrete for some type of a scale? So now we are already trained well enough to recognize this is going to be the flow chart for non-parametric analyses, and this will be the flow chart for parametric analyses with a transition when we fail on certain levels over to non-parametric types of analyses. So let's do the parametric first. If we have continuous data that pass the test for normality, and there's 1, 2, or 3, or greater than 2 treatment groups, if there's only one treatment group, we would just look at a correlation. If there are only 2 groups, we ask whether they are paired or unpaired. If it's paired, we do the paired t-test. If it is unpaired, we have to look at variance. If it is equal, we use the unpaired pooled variance t-test. If the variances are unequal, we use the unpaired t-separate variance test. If there are more than one treatment group and the variances are equal, we use the analysis of variance, and as we said, some type of a post hoc follow-up test for significant difference between the treatment groups. And we will look at some of those as I had stated before. If the variance turns out to be unequal, then shift, as with the non-normal continuous data, over to an ordinal analysis, a non-parametric, where if there's only one only one treatment group, then there is a rank correlation. And if there's 2, paired or unpaired, we would use the signed rank or the sign test for paired. For the unpaired, it'd be the rank sum and the median test. For more than 2 treatment groups, it would be the Kruskal-Wallis, which again is equivalent to the ANOVA. The signed rank and rank sum test, for example, are equivalent to the t-test that we're most familiar with. For the discrete data, you're going to have either 2 or more than 2 treatment groups. If you have 2 and they are paired, then a McNemar's test would be used. If they are unpaired or you have more than 2, then a Pearson chi-square could be used. This is that same table in black and white, which I suppose might have looked a little bit better in this discussion, but when you have printed out these notes, hopefully this one will be a bit easier to use. Well, this ends our discussion of the research design and data management for